Hello, Eastview Scholars, and welcome to this edition of Sharp Shorts, where we're going to talk about chemical reactions. We have now worked very hard in trying to write formulas and be able to name our ionic and covalent compounds. And this is the next step, because this really is what the course is about. Chemistry is about the interactions of matter and those chemical reactions that occur and those chemical changes that occur. And if you go back to Dalton and the principles that we looked at in starting atomic theory, one of the things Dalton said is chemical reactions occur when elements combine, separate, or rearrange. And that's truly it. Of all the billions of chemical reactions, there's only three things they can do. They can make something, they can break something, they can rearrange something. And that's what we're here to look at. Now, an equation is just the exact written equation. It tells what's going on in that reaction. So right in front of you, you have the equation that tells you. Now, all standard equations start with reactants. So the chemicals you start with are the reactants. And then when they make some new bonds, break some old bonds, rearrange some bonds, then you get new products, and that's what a chemical change is, if you recall back from everything we built on. Well, the equation tells you that in exact mathematical proportions. It has to be written that way. Those three laws, the law of conservation of mass, the law of definite composition, the law of multiple proportions that Dalton used to build his theories that said chemical reactions occur when elements combine, separate, or rearrange, or when he said elements must combine in simple whole number ratios. All those scientific theories and laws have to be written into the equation so you can look at it and see exactly what's going on at the atomic level. And that's why it says on the bottom here, all reactions must balance. You cannot create or destroy matter, law of conservation of mass, therefore you must have the same elements on each side. Now, the balancing portion we're going to do in our next video. This first portion is just to introduce the types of reactions. Now you'll see this again in our next video, but when I'm writing and balancing reactions, I think there are three key steps to follow. Number one, identify the type of reaction. This will help you. We're going to learn 5, and this will help you to understand how the atoms are going to interact, how they're going to either separate, combine, or rearrange, and it will help you understand the product. Then, when you do that, and this is why we did all our naming, then for ionic compounds and stuff, you need to write them properly to reflect everything we learned about balancing charges and combining in whole number ratios. And you have to remember your diatomic elements again, because there are occasions in chemical reactions where oxygen or nitrogen will be released and not bound up in a compound, in which case it'll bond. So you got to do that. The last step then is to balance the equation so that you have an equal number. You can't do number 3 without doing 1 and 2 first. So let's just basically look at number 1 and identify the types of reactions. Again, there's only 3 things you can do. You can make something, break something, or rearrange it. And in our study, we're going to look at 5 different types of reactions. The first one here is synthesis, or sometimes they're called combination. And that's putting something together. Now, the key to it is, if I want to identify it, as I say here, is look for a single product. Now, here's the general formula. I'm mixing A and B, and I get compound AB. That's just a single product. Here, and this is what we're going to look at 99% of the time, I mix nitrogen with hydrogen, and I make ammonia. That's a synthesis reaction. It certainly is possible that I could mix 2 compounds like magnesium oxide and water and make magnesium hydroxide. That certainly is a possibility in certain situations, or to have an element compound and make a bigger thing. But focus on the fact for us, this is good enough, that generally we're looking at 2 elements making a compound. I just want you aware that those things can happen. Okay, so that's making it. Now, breaking it is decomposing, and notice that the general equation is exactly the opposite of synthesis. You have one reactant, and that's kind of your clue. You have one reactant and it's breaking into its component parts. Now it can do it in a couple ways. Here we go where carbon monoxide is breaking into carbon and oxygen, its two elemental components. Here's one where carbonic acid is breaking into water and carbon dioxide, so it's breaking into smaller compounds. Again, now, either one of these is valid. These are a little easier to understand because you only have one reactant, or a little easier to recognize in synthesis because you have one reactant. But just that's my clue here. If I have one of these and then I see it breaking into component parts, that's a decomposition. Which leaves us then with rearrangement. And there's two things you can rearrange. You can have an element in a compound, and they're going to rearrange what they're hooked to. So like here, BC was the compound, A came in and bound with C, and B was then released as an element by itself. Or as you can see here, the equation for a lab we did earlier this year when we made copper, aluminum, which is a cation when it's charged, came in to replace copper, the cation in the equation of copper sulfite. So aluminum came in to replace the cation because it had the same charge and bind with the sulfate in the copper sulfate, in which case the copper was released, and you saw that precipitate to the bottom, and aluminum sulfate was what was dissolved in the liquid that was left. Okay? And that's a single replacement. It's just this cation replacing that cation to form a new compound. It is also possible here, as you look at fluorine as an anion, that fluorine could come into this compound and replace bromine, because that's the anion in this compound. And notice in single replacement it always wants to replace the like charge. And I make hydrofluoric acid and bromine. Now, in single replacement, so I recognize them because it's an element in a compound, but notice what it says here, check the activity series. If this is going to occur, then this element has to be stronger than the one that is in the compound, or in other words, it has to be strong enough that the sulfate would rather bind to the aluminum, or the hydrogen would rather bind to the fluorine. Okay? And so there's lists out there, and you have a list on your cheat sheet where the activity series, where lithium is the highest, gold is the lowest. It just goes in order of what's the strongest, and you look on that list to see. And if you look on that list, you'll see that aluminum is stronger than copper, so it would replace it. If it wasn't strong enough, then no reaction would occur, and you would have nothing in the product side. It would just, nothing would occur. You wouldn't see any chemical change at all. That list that you have on your cheat sheet is for the cations. And it's not all of them. It's enough to fit on your cheat sheet for quizzes and exams. For the anions, well, that's just the halogen row of the periodic table. Remember, there's very few anions. Almost the whole periodic table is positively charged cations. So there's only a few, and they go in order. If you go down column 17, the halogens, fluorine is the strongest, iodine is the weakest. So here, fluorine is stronger than bromine, so it will replace it because the hydrogen would much rather be bound to the fluorine. Our other possible rearrangement then is what's called double replacement, and here's what you can see. It's just the rearrangements of cations and anions in two compounds. So that's what makes it different than here, is that it is two compounds, AB plus CD. And what you notice here is, since all ionic compounds are written cation anion, you can see in our product side that A then bound to D, and C then went to bind with B. And here's an example below where the sodium, which is the cation, then bound with the fluorine, and the lithium bound to the chlorine. There are things that control whether that would occur, but we're not going to worry about that. We're going to assume that all double replacement reactions occur. And then as things come in to tell us why, or why it wouldn't occur, or why we wouldn't see a reaction, we'll add those in during the year. So of what we've learned, the only one we have to check and see if the reaction will occur are single replacement, the last one we did. The final reaction we're going to look at is a type of decomposition, but it's organic. It's combustion. This is what your car does when it's burning gas. This is what the wood does when you're sitting by a fire. Combustion is any hydrocarbon, which is just any mixture of carbon and hydrogen. Here you can see butane. So there's a certain number of carbons, a certain number of hydrogens. Sometimes there might be an oxygen in here. That's okay. But it is mixed with oxygen, or it burns an oxygen. If you know anything from maybe Scouts or wherever you might have learned about camping and building fires and stuff like that, you can't have a fire, the triangle, you got to have oxygen. You got to have a fuel, and you got to have oxygen. Combustion reactions, when they are finally all said and done and everything's all burned up, will produce carbon dioxide and water. On the way, they make smaller and smaller hydrocarbons until they get to carbon dioxide and water. The nice thing about combustion reactions are they are the easiest to recognize. They are the most difficult to balance, but you can see below here, butane plus oxygen makes carbon dioxide and water. That's always the products. That is always one of the reactants. The only variable here is what is the hydrocarbon, what is that organic carbon compound that you are working with. Anyhow, that's our 5 types of reactions, and that's step 1. If you can understand these reactions, then you understand what the product should look like when we ask you to write the equation. Same here. You should then be able to switch those. You should be able to switch these around if the element is strong enough to replace. You should be able to work out how to decompose this substance or how to put it together. That is the first step in being able to understand what's going on in a chemical reaction. Tune into our next video, which is going to talk about how to balance these equations. Until then, scholar up, Eastview.